Hello, everyone. So it is the last lecture of the semester. Yay. We are doing chapter 14. We're not doing the whole thing, just the bits and parts that are really important in chapter 14. So it's just going to be one lecture. And this will be covered on the final exam. Just make sure that you do, the homework problems that pertain to the material that's covered in this lecture. Nothing outside of what I teach in this lecture is going to be covered, right? So on the final exam. So it's only what um, I lecture in this video. All right, so let's get to it. Chapter 14 is on solutions. Um, and solutions, you guys have actually heard of that word already, but just a review, right? Solution is any time that you have two components or more of a mixture. And then in the mixture, you always have the thing that is in abundance or in the majority. We call that the solvent, right? And then the thing that's in the minority, we call that the solute. Okay, so salt water, for example, is a solution. It comprised of water and sodium chloride. Since it's mostly water, water is the solvent, right? And sodium chloride, since it's present in the minority, is called a solute. Okay, so that's how it is always, right? Um, Ethanol is another type of solution. Well, ethanol and water, so something like vodka or beer or wine, the stuff that we love to drink, right? All of those are solutions as well. But wine, for example, right, is mainly water. So water is still a solvent in wine, and then ethanol would be the solute, right? But in something like Bacardi 151, which is now 75% ethanol, all of a sudden it's ethanol that is the solvent and water is the solute, right? Okay. So why do solutions form and why does mixing occur? So you guys know this, you've experienced it in everyday life, right? That things just mix spontaneously. So in figure A here, let's say you have, two chambers that's separated by a barrier, and on the left side is all water, right? Pure water molecules. On the right side, you have seawater, you have salt water. Okay. So as soon as you remove the barrier, we know that eventually the seawater is going to come over to the left side, the waters come over to the right side. They're going to evenly mix. Okay. To a uniform concentration. Okay. So mixing is spontaneous due to molecular motion, right? The water molecules and the sodium chloride are constantly in motion. So given time, they will just spread out and mix with each other. Um, so that's just what nature does, right? That's what we've observed. Okay, so let's talk about the common types of solutions. There are um, three different types of solutions, and they can be in whatever phase, right? It doesn't have to be a liquid and a liquid or a liquid and a solid. It could be also gas. You can have gaseous solutions as well. So air is an example of a gaseous solution. It has about 20 components, 4 to 5 main components, right? But really 20 components in the mixture of air. Um, then you can have liquid solutions. That's like if you take a solid and put into a liquid, so seawater, or vodka, which is ethanol and water. You can also have gas and liquid, like club soda. And then you also can also have solid solution. So solid state. So something like brass. Brass is actually a mixture of copper and zinc, right? And when we think about solutions, well, I was thinking about the liquid phase, but it can be in any phase, right? So brass is actually a solution. And then other alloys as well. Okay, so some terms that you guys may already know, but let's review. When one substance dissolves in another, we call that soluble. So for example, sodium chloride or table salt is soluble in water. Bromine is soluble in methylene chloride. And if one substance does not dissolve in another, we call that insoluble, right? So for example, oil and water don't mix, so oil is insoluble in water. And what determines the solubility of one thing in another is going to be dependent on two main things. The first thing is the second law of thermodynamics. So this is just the law of nature, is that nature tends to want to mix. And this is the law of entropy. Everything tends to disorder. So mixing increases disorder. And so it just naturally happens, just like water flows downhill, which is a natural thing that occurs, right? Um, you learn more about this in Chem too, like thermodynamics, a lot of thermodynamics. But that's, that's all you got to know here, right? Is that naturally things want to tend to mix. And then two, it's the IMFs, right? So remember the chemist rule of thumb for mixing, like dissolves like. So polar things will want to be um, uh, uh, mixed in other polar things, and non-polar things will mix with other non-polar things, right? But polar things do not mix in non-polar things. Okay, so that's nature's tendency towards mixing. The word for it is entropy. Um, so nature wants to increase entropy, right? Just naturally, that's what the universe tends to do, is to increase entropy. So anything that would increase entropy or increase disorder, that will happen more naturally. Okay. And mixing does that, right? When you mix something, um, you actually increase disorder. Whereas like if you separate things out and you organize things is against entropy. Right. And so that's why that takes energy, right? For you to sort things or separate things, that actually requires energy in order to do that. But, you know, just letting things go to chaos is the natural way, right? And so even the universe is doing that, right? The universe is always increasing, and that increases entropy, right? So it's the measure of energy dispersal in the system, or I like to think of it disorder, right? Entropy is like disorder. Okay, so how about the effect of IMFs? How does that affect solubility? Well, remember, like dissolves like. Okay, so let's say we have, you know, um, water, which is the blue balls here, and then we have the solute. Let's say that's sodium chloride or something, as the red balls. In order for these two things to mix, there are some competing interactions. So obviously, with the water molecules, there's the solvent-solvent IMF, which would be hydrogen bonding in water, right? And then the solute-solute interactions of sodium chloride would be ionic, right? So both of these are highly polar, okay? So now to assess whether they will mix, we have to assess what would be the new IMF that forms between the two. Between the blue and the red, the solvent and the solute, there has to be also a strong IMF. Otherwise, there's no mixing. Okay. So it turns out between the blue and the red is ion dipole, right? Here's the ion, here's the dipole. And ion dipole is also a very strong IMF. And so that's why sodium chloride mixes with water, right? So in the at the end of the day, the analysis is it makes sense. The new interaction, the new attraction must be comparable to the old ones, or you're not going to get mixing, right? There's no reason why the waters would give up its hydrogen bonding to go with something weaker, right? Much weaker. So that's how it goes, right? If the solvent solute interactions is greater than the original IMS, then you have mixing, right? A solution will form, or at least comparable, right? At least equal to, then a solution is formed. However, if your solvent solute, the new interactions is a lot weaker than what was there, then you're not going to have solution formation. Okay, so we can actually measure this. We can quantify it. We can mass it out, right? Let's say you want to know how much salt can dissolve in water. Let's say you would have a liter of water, right? And then you start to mass out how much sodium chloride you can put into water before it doesn't dissolve anymore. And so this is what we call the solubility limit of a solution, the maximum amount of solute that can go into the solvent. And usually there's always a limit to a solid going into a liquid. But if you're a gas, since gases are, very far apart from each other, have a lot of space in between them, gases are always soluble in each other in any um, proportions. And there's a term for that. If you have two things that are always soluble or that are soluble in each other, we call that miscible. Okay, so alcohol and water, for example, are miscible, but oil and water are immiscible. Right. So just vocab terms that you want to know about. All right, so that's the chemist's rule of thumb, right? Like dissolves like. Polar compounds will dissolve in polar solvents. Non-polar compounds will dissolve in non-polar solvents. Okay. So if you just know that rule of thumb, you can actually predict solubility of compounds that you've never even seen before. So let's try it in this example problem. Now, remember in the last lecture, there were certain groups in a molecule that is hydrophilic. Remember that? Things that are very polar. And those would be, if you see C double bond O, OH groups, NH groups, chlorine groups, right? Those are very polar bonds. And so if you see those in molecules, most likely your molecules can be water soluble. But if you don't see that and you mainly see CC and CH bonds, then you're going to be fat soluble, right? So in these four compounds here, we are going to try and predict whether it's fat soluble or water soluble. Okay, so for vitamins here, let's start with vitamin C. Okay, how are we going to analyze this? Remember, the C double bond O or any CO bonds, they tend to be polars. I see like a polar region right here. OH as well, right? Because you can do hydrogen bonding here with OH. Oh, two more OH groups over here. Hydrogen bonding. So water has what kind of IMF? Hydrogen bonding. Vitamin C is very soluble in water, okay, for that reason, okay? Because it has all of these hydrophilic, right? All these polar groups around the molecule. Okay, we go to B, vitamin K3. Most of the molecules, you can see it already, just CC bonds and CH bonds. So non-polar, non-polar. This is non-polar as well. The only polar region are the C double bond O, but look where they are. They're opposite each other. So if you draw the bond polarity arrow pointing towards oxygen for this CO bond and pointing towards oxygen for this CO bond, they're pointing opposite directions. So the polarity cancel, right? And so what you get is non-polar. Okay, non-polar, it's not going to be soluble in water. It will be instead be fat soluble. All right, let's go to vitamin A. Okay, what do we see? Pretty obvious here, right? CC-CH bonds everywhere, non-polar. There's one OH group. That does a little bit of hydrogen bonding with water, a little bit. But most of this is going to be water insoluble. So we got to say fat soluble for vitamin A. Right? Vitamin B5. Okay. All right, I'm seeing a lot of OH groups, right? You see that? OH groups here and here. C double bond O, C double bond O, so polar, polar, NH. So lots of hydrogen bonding that can be formed here. So water soluble vitamin B5, right? So isn't that remarkable that, we are able to predict solubility, even though, we've never seen these structures before, right? But just knowing what we know about hydrophilic groups, we can correctly predict that. And that's important too, because in knowing how much of these vitamins that we need in our body, we know that we can't overdose on vitamin C or even vitamin B5, because if you have too much of it, your body will just get rid of it, right? Because it's water soluble, so you just like pee it out, right? Not a problem. However, you do have to watch how much vitamin K3 you take in and vitamin A, right? And so, of course, you should read the label on these. If you take supplements and things like that, you should read the label and make sure, for the ones that are not water soluble, that you're not overdosing on it, right? There's a limit to how much you can have, right? All right, let's keep going. Here's another practice. Which compounds are going to be soluble in hexane? Okay, now remember hexane is C6H14. Only carbon-carbon, carbon-hydrogen bonds. We know that hexane is nonpolar. Okay, so water, A, is not going to be soluble in hexane. Okay, that's pretty obvious. B, propane, and it gives you the chemical formula. You only see CC and CH bonds. Remember, those are nonpolar. So propane would certainly dissolve in hexane. Looking at ammonia, what kind of IMF? Mm, hydrogen bonding, right? So superpolar. That's not going to be soluble in hexane. Right? And then hydrogen chloride. That's polar, so that's going to be not be soluble in hexane. Okay, so let's talk about solution equilibrium. Solution equilibrium um, is a process in which um, we can describe how much of a solute can go into a solution. At one point, it does not dissolve anymore, right? And we reach what's called the solubility limit or solution equilibrium. So we can imagine, let's say sodium chloride dissolving in water. We can imagine that initially, this is the picture, right? So we have a beaker full of water and we drop in sodium chloride, table salt. Remember, table salt is existing in a 3D crystal lattice of sodium plus Cl minus. So initially, there's plenty of water to dissolve the sodium chloride. So the rate of dissolution, right, or dissolving is very high, right? So a very big arrow for dissolution, okay? And the arrow for recrystallization at first is not even there because there's nothing to recrystallize. But over time, as you have sodium plus and Cl minus floating in solution, they can recombine and go back into the crystal lattice. And so that's what recrystallization is. They turn back into solid state. Okay. But at first, right, the rate of recrystallization is smaller than the rate of dissolution. Um, until what happens? You have a lot of ions in solution. So the rate of recrystallization grows while the dissolution rate decreases until they are both at the same rate. So what that means is you still have salt dissolving, but you also have Na plus and Cl minus coming together and recrystallizing at the same rate. Okay. So what you've done is what's happened is you've reached solution equilibrium where the amount of salt that's dissolved stays constant. Right. Um, and so you can actually measure what this concentration is, right? And that's what we call the solubility limit um, of a solute, right? And the term for that, when you reach solubility limit, you say that the solution is saturated. It's saturated meaning it's full, right? So the water can't dissolve anymore of the ions, right? So that means if you add more solute, it won't dissolve, it'll just collect at the bottom of the beaker, okay? Other terms, right? Before the saturation limit or solubility limit, the solution is called unsaturated, meaning if you add more solute, it will still dissolve. Okay. Then you can also have solutions that is over the saturation limit, and we call that supersaturated. So what that's kind of weird. How do you make a supersaturated solution? Right? That means how do you trick the solution into taking more than it can? Usually that's done with temperature. Okay, so if you heat up solution. And we know that heat injects kinetic energy into the molecules. And so the water molecules are vibrating and moving at a faster rate. So then it can take on more solute, right? So it'll dissolve more solute. Um, and then you let it cool down very slowly. Okay. And then at one point it just crashes out, right? So it remembers that it is super saturated. So any sort of if you bump into it or you give it a seed crystal, all of a sudden it will crystallize out. So there's a temperature dependence on solubility, right? If you have, and I'm sure you've experienced this in real life. Say if you have a hot drink, like a hot coffee or a hot tea, you can definitely put more sugar in it than if your tea is cold or your coffee is cold, right? And the rate of solubility is also faster as well. It's like much quicker to dissolve in a hot liquid than cold, right? So so when a solubility limit is stated, it is also imperative that the temperature is stated as well, because the solubility can change with temperature, right? And it's usually measured in grams of the solute per 100 grams of water, which is the solvent. Okay, so here's some solubility curves, and it's pretty general, right? As you can see from the graph, that solubility, which is on the y-axis, increases as you increase the temperature, which is the x-axis here, right? So most ionic compounds are curving up, right? But you always have some exception, right, to the rule, and that's cerium sulfate here. Right? Cerium 3 sulfate actually decreases in solubility as you raise the temperature. Yeah. And the reason for this is the cerium 3 plus is actually a quite large ion, so it's going to attract a lot more water molecules around it when it's in solution. So it actually goes against entropy. Okay? And so that's why solubility decreases as you increase temperature. Okay, what about gases? Solubility of gases, how temperature affects that? Well, remember, gases move a lot quicker than liquid, right? So in order to put a gas into a liquid, right, you actually have to it takes effort, right? Because gases are like moving all around a lot faster. It doesn't want to be in a liquid, okay? And so that's why when you open, say, a can of soda, you can hear and feel the gases leaving the liquid phase because the gases are wanting to escape, right? It's traveling at a lot faster speed. So what does that say about temperature dependence on the solubility of gases? Well, as you increase the temperature, that means the gases are going to want to even leave the solution even faster, right? So the solubility of gases will decrease with increasing temperature, right? So it's the opposite of a solid. Right? Um, and you guys have experienced this in real life as well. Cold soda pop tastes a lot better than warm soda, right? Because in warm soda, a lot of the carbonation has left the solution, so it tastes flatter. Right? Okay, so that gets us to Henry's law here. Henry's law um, tells us that the solubility of a gas is directly related to the partial pressure of that gas in solution through Kh, which is called Henry's constant. Henry's constant can be found in any table, any textbook, so you don't have to, know it's already been measured for you. And Henry's constant is tied to an individual gas, right? So each gas has its own constant. So the equation is quite simple, all right? And it's on your equation sheet too, okay? Let's do an example problem so you see how you use Henry's law. So this question asks, what pressure of carbon dioxide is required to keep the carbon dioxide concentration in a bottle of club soda at 0.12 molar at 25 degrees Celsius? Okay, so let me write all this on the board. And Henry's equation. So solubility is Kh times partial pressure of the gas. So since it's talking about CO2, we have to look up the Kh for CO2. So it is 3.4 times 10 to the minus 2. Notice the units, it's molar per ATM. Okay. Okay, so let's do it. It's asking for partial pressure of the CO2. Okay. At what partial pressure of CO2 do we need to have 0.12 molar? Okay. So we're going to solve for P gas. Just do a little algebra here, right? P gas is equal to the solubility over Kh. And solubility, unless it's stated otherwise, guys, is always going to be in molarity, remember, which is moles over liter. Okay, so that's already given to us. So we'll just go 0.12 molar. And we're divided by Kh for CO2. Just grab that number, right? 3.4 times 10 to the minus 2. molar per ATM. So molar cancel. 1/1 ATM is the same thing as ATM. Okay, so let's plug that into our calculator. 3.5 ATM. Two sig figs, right? Because of this number. Okay. All right. So what are we saying? Well, in order to get, this club soda to, be fizzy and to have this molarity, this solubility, we need to put 3.5 atmosphere of CO2 into water, right? Into the solution. In order to get this solubility, which is quite a bit more than where we're at, right? Where we're at is 1 atmosphere. And so, that's why you need something like a soda stream in order to carbonate, because it just won't do it spontaneously, right? I mean, there's CO2 in the atmosphere and it's 1 ATM, right? Where we're at. But if you take a water bottle and you put it there, you're not going to carbonate it, right? It's not going to get carbonated. It's only at 1 ATM. So you have to really push the CO2 into the water. And how much would you need? A pressure of 3.5 to get it to carbonate. And so that's what a soda stream does, right? It's providing 3.5 atmosphere. Okay, let's move on. So concentrations. So since we are talking about solutions, we do need a way in order to measure how concentrated a solution is, right? Just like I want to know, like how strong is the beer, right? That's a concentration unit too. If you're talking about 6% alcohol, 9% alcohol, right? Your double IPA or 12% alcohol, which is your wine. All of those numbers are telling you how concentrated ethanol is. You know how strong the solution is, right? But there are different concentration units. One of them you already know, which is molarity, right? And that's moles over liter. So that you can tell, right, how concentrated is the solution or how dilute it is, right? So molarity, we already know. That's in this table, the top one, okay? Molarity stands for moles over liter, and the unit, right, is molar or big M, okay? That's the abbreviation, right? Is big M. That's just one of the concentration, right? There are many. So we are gonna go through and we'll make sure we know each concentration term here. This is the main part of this last chapter, okay? So the way that I would suggest to you to study this is do flashcards, right? Because these terms are new now, okay? So you want to make sure you know what molality is. Maybe write on one side of the flashcard, molality, and then on the other side, you write moles over a kilogram, right? So there'll always be a top, but there'll always be a bottom, right? So make sure that you have that. So molality, and also tricky here, right? Because it's only different by one letter. Molality is little m, and it stands for mole on top, mole of who? Of the solute over kilogram of the solvent. Okay. Notice how that's different than molarity. Okay. The top is the same for both, but in molarity, it's liters of solution, of the entire solution, whereas in molality, it's kilogram of just the solvent. Okay. So pay attention to that. The third one is mole fraction. And actually, you guys already know mole fraction from the gas law chapter, right? Mole fraction is the amount of solute in moles over the total amount of moles, meaning the mole of the solute plus the mole of the solvent. And since they're dividing each other, moles cancel. So mole fraction has no units, right? If you recall, mole fraction does not have a unit. Then we get to mole percent. The percent comes from the fraction, right? Just like 1/2 is 50%. Same thing here. So just look at your mole fraction, and then you multiply it by 100%, and then you get your mole percent, okay? So you'll always need to do a mole fraction first before you can get to a mole percent. Alrighty? All right, and then the last one is parts by mass. And there are three different ways that you can do parts by mass. Parts by mass, you already do one of them. It's called percent, right? Percent is a parts by mass. But basically on top is the mass of the solute. On bottom is the mass of the total solution. And then you multiply by some multiplication factor. The percent, when you do percent mass, the multiplication factor is 100. You know this already, right? It's just these bottom two are new. So now if you want to do parts per million by mass, then the multiplication factor is 1,000,000 or 10 to the 6. If you want to do parts per billion, then your multiplication factor is going to be 10 to the 9. Okay. And the abbreviation ppm versus ppb, you may have heard, seen this before, right? ppm means parts per million, ppb parts per billion. Um, we use percent a lot, but there are times where you would need to use, where it's more convenient to use ppm or ppb, especially when you're talking about a very dilute solution. It would make sense to, it's less convenient to do it in percent, right? So that's why you should know all of these, okay? And then there's parts by volume. That's the very end. So instead of a mass percent, it's a volume percent. So volume of solute on top, divide by volume of the solution, times the same multiplication factor here, right? If it's percent by volume, then it's 100, right? If it's parts per million, then it's 1,000,000. Parts per billion, then the multiplication factor is 1,000,000,000. All right, so let's go through each of them. We want to make sure that you know how to calculate each one of these, and then also convert between different concentration units, okay? That's really the main part of chapter 14. All right, so again, molarity, right? That one we know already. Mole of solute on top, liter of solution on bottom. Okay. And big M is your abbreviated unit for molar, right? Okay, molality, which is abbreviated by little m. Remember, again, it's mole of solutes on top, just like in molarity, but on bottom, it's kilograms of solid. Okay. Kilograms of solvent. So why do we need molality versus molarity? They look very similar. And actually, their values are going to be quite similar as well, right? But the reason why we introduce molality is that the denominator, the mass, is not dependent on temperature. It does not vary with temperature. So that's kind of nice to measure things in molality because you don't care about what temperature the solution's at. Okay, with molarity, we know that from PV equals nRT, if temperature is high, then volume's also high, right? So that means the molarity will change with temperature, and that's really inconvenient when you're trying to do a calculation, right? Or you're trying to do chemistry. So if you use molality, you know that the value can never change. It doesn't matter what temperature you're at. You can measure molality and it doesn't change. Okay. All right, and then we got parts solute and parts solution. Okay, let's look at percent. Okay, we can break that down. Percent is cent, like century, is 100. So percent is per 100. Okay, so parts per 100, right? So just like your exam, right? You get 70 points out of 100 points, then that's 70%, right? 70 out of 100. So the multiplication factor then is going to be 100. Parts per million, you go mass of the solute, divide by mass of the solution, times 1,000,000. Parts per billion, on top, mass of solute, bottom, mass of solution, times billion. And then mole fraction, okay? Remember mole fraction? It's just a fraction, right? So part over whole. So the part would be the solute, right? So moles of solute on top over total mole. That'll give you mole fraction. And remember the symbol for it too. It's chi, right? That stands for mole fraction. So mole fraction of A here would be moles of A over total mole, Okay. Once you get the mole fraction, if you multiply by 100%, then you also get what's called the mole percentage. Right? Often they're asked together, right? You're asked to calculate the mole fraction first, and then you'll ask for the mole percent. Okay, so next we're gonna go and convert between these concentration units. So to convert from one unit to another, just look at what's desired, right? Look at what you have now, which is what you start with, and then what it wants you to convert to. You want to notice what's on top and what's on bottom, right? It's always, there's a numerator, and there's a denominator. And you change, or you convert one at a time. Don't try to do both at the same time, right? Just be like, all right, I'm gonna try and get the numerator to match what I want in my desired unit, and then I'm gonna try to make the denominator match what's desired, right? The unit that's desired. Okay, so let's do this problem first. What volume in milliliter of a soft drink that is 10.5% sucrose by mass contains 78.5 grams of sucrose? And then it gives you the density of the solution as well, 1.04 grams per mil. Okay, so let me put this on the board. So we have 10.5% C12H22O11. And then it's asking how much of this contains 78.5 grams of C12H22O11. The density of the solution is 1.04 grams per milliliter. So here we go, 78.5 grams of C12H22O11. And what we want out is the amount of solution, okay? So we can translate this. If I have 10.5% of sucrose, I can break that down. It means that I have 10.5 grams of C12H22O11 per 100 grams of the solution, okay? So that is actually your conversion factor. And if you break it down like that, now it makes it really easy to apply, right? You want solution on top, so 100 grams of solution over 10.5 grams of C12, H22O11. Remember, you want this to cancel, right? And then it's asking you the volume, right? So how do we get from grams mass to volume? Use the density, okay? So grams on top right now, we want volume on top, so that's milliliter, 1 milliliter over 1.04 grams of the solution. Right. And that's it, right? It wants it in milliliters, so that's all we gotta do. 78.5 times 100 divided by 10.5 divided by 1. 719 milliliter of the solution. Okay. So that's the answer, right? You need 719 mils of the sugar solution to have 78.5 grams of sucrose of the sugar. Okay. All right, more practice problems for you guys, so you should do those. But yeah, let's move on. So in this problem here, it's asking us, it's giving us information, and then it's asking us to express it in different concentration terms. So this is great practice. Definitely something like this on the final exam, right? So let's read the information, and then we'll just basically have to convert the right to the right numerator and denominator, right, for each. So we got 17.2 grams of the ethylene glycol, that's our solute, in 0.500 kilograms of water. That's our solvent, right? It says the final volume is 515 milliliter. Calculate the concentration of the solution in each unit. Okay, so again, let me put the info on the board. Then 17.2 grams of C2H6O2 in half a kilogram of H2O. Final volume 515 milliliters. Okay, and then it wants molality, percent by mass, mole fraction, mole percent, in that order. Okay, so molarity first. So again, right, you gotta know what molarity is. It's big M, right? It's equal to mole of who? Mole of the solute over liter of the entire solution. Okay. All right, so do we have moles of solute? No, but we can figure it out because we have grams of solute. Okay, so we need to know the molar mass of that. Get the moles. So let's do that off to the side here. That's 17.2 grams of C2H6O2. 1 mole of C2H6O2. Let's calculate the molar mass. $62.07 grams of C2H6O2. Zero point 2771 moles of C2H6O2. Okay, so that's gonna go on top. 0.2771 moles. Divided by the liter of the solution. Okay, that's the volume, right? Well, we have a volume here. It's in milliliters, which is converted to liters, which is 0.5 liters. So what is the molarity of the solution? 0.538. 3 sig figs as well. C2H6O2. Right? Be very specific. What is the solute, right? Okay. Pretty straightforward, right? In B, it asks us for molality. Remember, molality is little m, and on top will still be moles of solute, but on bottom is kilograms of solvent. Okay, so easy. We already got the moles on top, 0.2771 moles. Now the kilograms of the solvent. Who's solvent? Solvent's water. Oh wait, we already have a kilogram there. Great. So it's just 0.500 kilograms on bottom. Which is 0.554 little m C2H6O2. Circle that. C, it was percent by mass. Percent by mass. Percent by mass is going to be grams, right, of solute over grams total times 100%. Okay, so what's the grams of the solute? 17.2 grams over the total grams is gonna be grams of the solute and the solvent. The solvent is in kilograms, so just multiply that by 1,000. We get 500, right? So 17.2 gram plus 500 grams at the bottom times 100% is equal to 517.2 at the bottom times 100, 3.33%. C2H6O2. 3.33. Okay. Next one, mole fraction. Mole fraction is mole of solute over mole total. So we had the moles of solute. We had it earlier, right? 0.2771 mole. Mole total, we'll have to take the mole solute plus water in mole. But we don't have water in mole. We have mass though. So all we have to do is turn it into grams and then divide by the molar mass of water, which is 18.02 grams per mole. Okay. So 500 divided by 18.02 is 27.75 moles of H2O. Okay. So now we just add it to here. Notice mole cancels out with mole. So your mole fraction is always unitless, right? All right, so 0.2771 divided by memory recall here, so 0.00989 C2H6O2. Okay. So mole fraction. And then lastly, it wants the mole percent. So then we take mole fraction times 100%. So this number, 0.00989 times 100% is 0.989%. C2 percent mole C2H6O2. Okay. So notice I specify, right? If it's a mole percent, I really need to write mole there. If it's just percent, by default, if you just see percent, it's a mass percent. Okay. If it's a mole percent, it would be spelled out to you as such. Okay. Yeah, so as you can see, all you need to really know here is what are the definitions for each of these? Right, what's in the numerator, what's in the denominator, and then just convert. It's just a simple fractions for all of these, right? Okay, let's go back to the slides. Okay, so make sure you do these problems as well. It's a different numbers here, but the same idea, right? So make sure you go to each one of these. Yep. All right, let's do this one together. What is the molarity of a 6.56% by mass glucose solution? The density of the solution is 1.03 grams per. All right, so again, 6.56% C6H12O6. And the density is 1.03 grams per milliliter. And it's asking, what is the molarity? Okay. Let's see how we can do this. All right, so what is desired? Molarity, which is what? We want out moles over liter. Okay. At the end, right? What do we start with? We start with the percent mass. Remember, we can break this down. 6.56% means 6.56 grams of C6H12O6 over 100 grams of solution. Okay. So here it's, right, we need to convert to moles of C6H12O6 and liters of solution. That's what we're asked to do. Okay. So remember what I said? Don't try to do both at the same time. Just separate it. The top needs to go to mole, so do that first. And then the bottom needs to go to liter. Okay. So make the top match first before you do the bottom. Okay. So start with 6.56 grams of C6H12O6 over 100 grams of solution. I'm gonna turn the top into a mole, so I need 1 mole of C6H12O6. And then down here would be the molar mass, right? So let's calculate that. So the bottom is 180.16 grams of C6H12O6. So that cancels out. And then we need grams of solution to turn into liter. Okay. So liter of the solution has to be on bottom. Now, how do we get from a mass to a volume? Oh, that's why we're given a density. So 1.03 gram wants to be on top, right? Because we want the volume on bottom. That's per milliliter of the solution. Okay. So that cancels. Okay. And now we want this milliliter to become a liter, right? So 1,000 milliliters on top and 1 liter on bottom. Okay. And all of a sudden we have what we need, moles over liter, right? You see that? How we did that step by step. Okay, so now let's punch it in. Zero 0.375 molar of C6H12O6. 3 sig figs, right? Because of that number. All right, let's go back to our slides. Okay, and then let's just do some practice, right? Some practice here. Hey, what is moles of solute over mole of solution, everybody? Molarity, okay? Ooh, what's mole of solute versus over kilograms of solvent? Molality. What is mass of solute over mass of solution times 100%? Mass. Mass of solute over mass of solution times not 106. This is a typo. It's 10 to the 6th power, so times a million. It'll be parts per million. Moles of solute over liter of solution. Molarity, right? Oh, wait, didn't we have that earlier? Oh, no. Okay, sorry. The first one, moles of solute over moles of solution, that was mole fractions. I read that wrong. Okay, and that's why I was like, wait a minute. Here it is. So moles of solute over liter of solution is molarity. Mass of solute over mass of solution times not 109, 10 to the 9th power. That's a billion. So it's parts per billion. Moles of solute over moles of solution is mole fraction, right? Times 100 will give you percent mole. Alrighty. Now this gets us to the last part of this lecture here, colligative properties. So what colligative properties are properties that only depend on the number of solutes of particles and not what they are, not what their identity are. So it doesn't matter what kind of particles you have, as long as it's dissolved in the solution, you will get these colligative properties. All right, so let's, before we can understand that, remember vapor pressure? Remember what vapor pressure was? After you reach dynamic equilibrium, the headspace above any liquid will have a certain pressure. We call that the vapor pressure of that liquid, right? And the vapor pressure of a liquid it can vary based on whatever the liquid is, right? And that has to do with its IMF. Remember that? If you have really strong IMF, that means it's harder to get to the gas phase. So stronger IMF leads to a lower vapor pressure. Whereas weak IMF leads to a higher vapor pressure. Because if you have a weak IMF, it's easier to put the liquid into the gas phase. All right. So now we think about vapor pressure. It's the same idea, but we're not doing it just for one thing. We're doing it for a mixture. So vapor pressure of a solution. Okay. All right. So let's say, now the blue balls the water. Okay. And the red balls are now your salt, table salt, sodium chloride. Right. So you have to think about the IMF, right? The new IMF with water and salt and see how it compares to just water alone. We know that water alone, IMF is hydrogen bonding, right? Um, so what is water and salt? You guys know this too. Salt is the ion, water is dipole. So ion dipole. Oh, the IMF, the new IMF is actually stronger than water's IMF, right? The solvent. And so what's going to happen is you're going to have an increase in the um, boiling point of the solution. Why? Because a stronger IMF means a lower vapor pressure, right? And so you have to add more energy to put things into the gas phase. Okay. So you will have a higher boiling point for a solution than you would the pure water. Okay. Okay, so this is an interesting situation to think about. Let's say that you have this little jar, and inside you got two beakers. The left beaker only has pure water, and the right beaker has salt water. Okay. Um, the question is, after a while, after these two are placed in the bell jar, what's it gonna look like as far as the level of solutions in each beaker? Well, the concentrated solution, right, the salt water is gonna have a lower vapor pressure. The pure solvent will have a higher vapor pressure. So the water is gonna move into the concentrated solution. So over time, what's gonna happen is the volume of the pure solvent in the left beaker will go down, while the volume of the right beaker goes up, right? And it'll just do that automatically, right? Due to the difference in vapor pressure. Okay, so this phenomenon can be described by Raoult's law. Raoult's law is very simple, actually. All it says is the partial pressure, which is P, right? The partial pressure of the solvent in solution is equal to the mole fraction of the solvent times the vapor pressure of uh of the solvent normally, right? Without being in the solution. Okay. Um, so let's, for example, calculate um the vapor pressure here at 25 degrees Celsius of a solution containing 99.5 grams sucrose and 300 mils water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. Assume the density of the water is 1.00 grams per mil. All right, so remember Raoult's law, very simple, right? The partial pressure of the solvent in a solution is the mole fraction of the solvent times its normal vapor pressure. So it gives you the normal vapor pressure of water here, right? It's 23.8 torr. Um, now we need to get Chi's solvent. Mole fraction of the solvent, we'll have to get moles um, of the whole thing, right? Uh, and that's the denominator. Then we get moles of the sucrose, and that's the numerator. That's how we get the mole fraction. And then times by 23.8. Okay. So let's do that. To get moles of the sucrose, we take 99.5, divide by its molar mass, which is 342.30, right? So this is how we get the moles of sucrose. To get the moles of water, remember we had 300 milliliters of water, and we know the density of water is 1 gram per milliliter. So that means we also have 300 grams of water, right? And then we divide by 18.02 grams of water to get the moles of water. Okay, so now we have the numerator, which is the moles of water, okay, over the total moles, which is these two numbers put together. So the moles of water is 16.65, divide by the total moles. This gets you your mole fraction, and then you multiply by the normal vapor pressure of water, which is 23.8 torr. So what you get is 23.4 torr. So we can see, right, that a solution will always have a lower vapor pressure than the pure solvent. And that's why for a solution, you'll always have a rise in boiling point. Okay, we're going to skip this. You guys don't have to know two-component solutions. Okay, so at the end of the day, what happens is, and here it shows you the phase diagram of a solution, which is in red, versus the pure solvent. What happens is because you have a solute that's dissolved, you have vapor pressure lowering. That means that will end up becoming boiling point elevation, right? So if you look, if the vapor pressure is lower, that means you're going to have a higher boiling point, okay? And then on the freezing and melting side, you actually will get a freezing point depression, okay? Now this is really interesting, but the way to think about this, again, let's use salt water as an example. If you have salt water, right, of course, you're going to have a boiling point elevation because the salt water has a lower vapor pressure. Okay, we already went over that. But why the freezing point depression? Well, let's think about what freezing is. If you just have pure water, right? Freezing is when you take kinetic energy away and um, uh, 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 the water molecules get closer together and the IMF strengthens, right? And so these water molecules find each other, the hydrogen bonds get set, and boom, it becomes a solid, right? As you take energy away, right? As you cool it down, that IMF strengthens and boom, right? You're locked in. That's what a solid is, okay? But now if you have a salt water solution, you're trying to freeze that. The problem is you have all of these sodium plus and Cl minus in between the water molecules. So it's harder for the water molecules to find other water molecules to do that hydrogen bonding because it has all of these ions in the way. So that's why you have to drop the temperature even more in order to get that whole entire solution to freeze, right? So what that means is it's harder to boil a solution. Not only is it harder to boil a solution, it's also harder to freeze a solution, right? Compared to just the pure solvent, okay? So that's what we call freezing point depression and boiling point elevation. Okay. And now we have equations for that as well, so that we can actually quantify by how much we shift the boiling point and the freezing point of solutions compared to the pure solvent. Okay. So these equations are super simple. Again, they're on your equation sheet as well. So let's look at the freezing point depression equation first. It's simply delta TF, which is the shift, right? The change in temperature of freezing is equal to little m, which remember is molality, times Kf. Kf is another constant that you can look up. It's called the freezing point depression constant. And it's measured in degrees Celsius per molal, okay? So you see that here for, in this table, right? There's just 6 random ones, but, you can look in the book, you would have, more of these. So if it's Kf, this is the column you would read. And if you're looking for boiling point elevation, it's the same um, equation, right? Change in the boiling point temperature. That means this is the shift. This shift in boiling point is equal to molality times Kb, where Kb is the boiling point elevation constant, and that you can find in the last column. Also, units are degrees Celsius per molal. Okay, so let's do an example problem so you guys see how that works. Pretty straightforward here. Really simple equation, right? And on the exam, of course, I would give you the constants, okay? So it's saying calculate freezing point of a 1.7 molal ethylene glycol solution. All right. So I would go, right? So my equation, it's about freezing point. So delta TF is equal to little m molality times KF. The KF for ethylene glycol, I'll look up on the table. Actually, not of ethylene glycol, we need to know the KF of the solvent. So the solvent here is still water. So we're looking for water on that table. KF is 1.86 degrees Celsius per molal. Yep. Okay, so delta TF is equal to molality is 1.7 molal times 1.86 degrees Celsius per molal. Molal cancels. 3.2 degrees Celsius. Okay, so right here is not the answer yet because this just tells you the shift. Okay, what it's asking for is calculate the new freezing point. So you have to ask yourself, what is the freezing point of pure water? We know that it is 0 degrees Celsius, right? So since we know that it's a freezing point depression, 3.2 tells you that that's how much it is lower than 0. So that's why you know how to subtract 3.2 degrees Celsius. So it's negative 3.2 degrees Celsius is the new freezing point. Right? Makes sense, right? Okay. Let's do the next problem for boiling point elevation. It says, what mass of ethylene glycol, 8 grams, must be added to 1 kilograms of water to produce a solution that boils at 105 degrees Celsius? Okay, so we have boiling point is 105 degrees Celsius. And we have a kilogram of water. There's the other stipulation. Okay, so what mass of ethylene glycol in grams? Okay, so what mass of C2H6O2? That's our question. Okay, let's do it. So boiling of the solution is 105. Well, we know that water boils at 100. So that means that our delta TB is 5 degrees Celsius. And that is equal to little m times KB, right? Looking at what KB is for water on that table, it's 0.512. So we have to solve for little m. Little m is going to be equal to 5 degrees Celsius, right? Or let's just do it in as the algebraic expression first, right? Little m is equal to delta TB over KB, where we know delta TB is 5 degrees Celsius, divide by 0.512 Celsius over molal. So Celsius cancels. 5 divided by 0.512 9.77 molal. And remember what molal is? Molal is moles of C2H6O2 over 1 kilogram of water. Okay, and then it tells us, right? It's actually 1 kilograms of water, so we'll multiply by 1 kilogram of water, cancel that out, and we'll get moles of C2H6O2, but it wants mass. So we multiply by the molar mass, 1 mole of C2H6O2 on the bottom. .07 grams of C2H6O2. .606 grams of C2H6O2 should be our answer. Yeah. Okay. All right, so back to our slides, and our last topic here is on osmosis. Okay, so the osmosis is the flow of solvent from a solution of low concentration into a solution of high concentration. Usually the solutions are separated by a semi-permeable membrane, and what that is, it allows solvent to flow through, but not solute. So the osmotic pressure is measured as pi, capital Pi is equal to big M times R times T. And this is how it works. You don't have to do calculations, all right? Just know the concept of osmosis. So here on the left picture, this is initially, let's say you have a semi-permeable membrane where the left side is salt water and the right side is just pure water. So what's going to happen is it's going to allow for exchange of the solvent only, right? And not the solute. So it's actually the water, well, the pure water is going to go to the left, right? It's going to go to dilute the salt water on the left side. So just spontaneously, you'll get a water level rise on the left side and a decrease on the right side because the water is just spontaneously rushing to the left side in order to make the left side less salty, right? And so that pressure of water coming to the left side, that's what we call osmotic pressure. Okay. And so again, osmotic pressure is occurring when you have two different concentration of solutions separated by a semi-permeable membrane. All right, so that's it, guys. That's it for chapter 14. That's all you need to know to do the final. Okay. So short chapter, basically the main thing is practicing those concentration units. All right, guys. Good luck studying for the final. I'll see you then.